Hey, welcome back. In this video, we're going to tackle the concept of improper integrals. And I have to admit, for me, improper integrals hold a special place. It's such a cool concept, and this is introducing you to a bigger concept that if you move on with calculus and analysis in mathematics, you're going to see this concept over and over. The main concept in this section is convergence and divergence. There are two main types of improper integrals. In this video, we're going to tackle the type 1. In this case, we're going to consider areas or definite integrals that cover infinite domains. To help us frame this concept, I want us to consider the graphs, specifically the areas under these two graphs on these infinite domains. In this case, we have f of x is 1 over e to the x on negative 2 to infinity. And over here, we have f of x equals 1 over x on 1/10 to infinity. In both of these cases, we're considering an infinite domain. So again, we're considering the areas under these curves from these. We have these finite left-hand points or these starting points for our interval, but we're unbounded in this case. The interesting question I want you to think about before we get into the math of this and kind of show some definitions and prove this fact, the question is, which of these areas is larger? And not only that, which area is larger and how much larger is it? If we can zoom out a little bit, you might get a better idea and some idea of which is larger. What we're going to prove in this video is that this area is what we call convergent. We can calculate the finite value of this area. The area under the curve of 1 over e to the x from negative 2 to infinity is about 7.4. Comparing that to the area under the curve of 1 over x from 1/10 to infinity, this area is what we call divergent. It's infinite, it's unbounded. The interesting thing about both these cases, if you consider this, and this is the deeper concept that you can see later in mathematics, is that this function goes to 0 quick enough to get an actual value. We can calculate the area. This function never reaches 0 fast enough, and therefore the area continues to grow unbounded. And all of that with the main idea that neither of these functions ever reach 0. It's not possible for this function or this function to output 0, though we can calculate that area. And I hope before we jump into this, you're thinking, no way, that doesn't make any sense. How does that make sense? Check this out. With your understanding of definite integrals and our definition using limits, you're going to see that it makes absolute sense, and it's pretty easy algebra once we get going. All right, we need to back up those pretty outrageous claims I just made. Let's do some work. First of all, we want to define these objects, right? So in this case right here, this first one is of the case that I was just showing you. We have the starting point for our interval, but it's on an unbounded interval going to infinity. In this case, what we mean by this is the following statement. We're saying that we're going to consider the integral from a to t of f of x dx, and then we're going to let t go to infinity. So again, that's what we're defining this statement as this right here. And that's really important because the way that we've defined the definite integral doesn't allow for us just to plug in an infinity. So this is actually a limit statement. The same thing here, but in this case, we have this b value and we're going to let t be the lower bound and it's going to go to negative infinity. So then, in their nature, these improper integrals are simply limit statements. And so in this case, if the limit in each of these cases is finite, if we get a value out from it, then we say it's convergent. And if the limit is not finite, we say it's divergent. And it's important in more layman's terms to understand these statements, convergent and divergent, simply mean if you're looking at this infinite limit, your function falls down to 0 fast enough or it converges with the x-axis so you get an actual value. So even though you have this unbounded infinite interval that you're looking at, it goes to 0 fast enough for us to get an actual value out of the area under that curve. If it's divergent, it means it's not going to 0 fast enough on these infinite scales, these infinite intervals, and so we cannot actually calculate a value for that area. And finally, this last statement, if we have an infinite interval over all real numbers from negative infinity to infinity, what this actually means is simply the combination of both of these. So what we're going to say in this case, this is the integral, the limit, as t goes to negative infinity of the integral that goes from t to a, right? So negative infinity to a, that's this definition right here. So of our function f of x. And then we add to that the integral that goes from a to t, where t, as said above, goes to infinity. And importantly to say is the convergence of this one statement right here depends on the convergence of both of these. So to actually be able to calculate, to say that this limit exists, to have that this function has a value from negative infinity to infinity, or the area under the curve, it means both of these sides from any a value. It's really important. We often will use 0 or something easy to calculate, but from any a value, you break it up and then you go to infinity and negative infinity. You add those areas together. Both of those areas on both sides have to converge for this improper integral to be convergent. Lastly, before we start hitting examples, I want to really emphasize these definitions that you have them down. We're going to start using the words convergent and divergent constantly. And in fact, you're going to see these in Calc 3 and beyond. They're important words, but they're really simple definitions. They can seem really overbearing and really difficult. But again, convergent in this case for an improper integral simply means we can get out a finite value. Divergent says it's not possible. It's an unbounded area. All right, now that we have the particulars out of the way, as promised, I want to revisit these two that we was talking about at the beginning of this video. In this case, we're being asked to evaluate the improper integral from -2 to infinity of 1 over e to the x. Importantly, before we do anything, we want to rewrite this in our limit statement. So what this means as a usable object for us is that if we let t go to infinity, this is the integral from -2 to t, and importantly, just so it's useful when I'm actually doing this, I'm going to rewrite this as e to the -x dx. And at this point, all we need to do is evaluate this integral. The awkward part is having this t here, but as you're going to see, what this is going to create is a fairly simple algebraic expression that then I'm going to evaluate the limit as t goes to infinity. So in this case, again, the limit here is just going to hang out. It's not doing anything exciting quite yet. In this case right here, the antiderivative of e to the -x would be negative e to the -x. I get that negative factor out from anti-differentiating or differentiating, just the way that e to the x generally works. And we're going to evaluate that from t to -2. And then moving straight along here, what I'm going to do is plug in those bounds. So I have negative e to the -t minus negative e to the -2 or +2. All right, so that's the difficult integral work. What I'm going to do now is just apply this double negative right here. This is a constant term, e squared, in this case, and then I'm going to rewrite this as 1 over e to the t, just to make it easier to think about when I'm calculating this limit. So I have the limit as t goes to infinity of -1 over e to the t plus e squared. Now all I have to do is calculate the limit, and then as t goes to infinity, we would know that this term goes to 0. This is a constant term, and so this area under the function 1 over e to the x from -2 to infinity has an exact value of e squared, which is about 7.4. And as previously stated, because this comes to a finite value, we say that this improper integral is convergent. And then to put a button on that original conversation that we had at the beginning of this video, here we have the integral from 1/10 to infinity of 1 over x. And my statement is, while the integral from 1 over e to the x from negative 2 to infinity is a nice, neat, small number, 7.4. This is an infinitely large area. And so what we're going to do is simply put in that definition. So we're going to put a t value here and have t go to infinity. And again, hopefully you appreciate this trick, and it's important. I mean, the reason we're putting a t in is so that we actually have something to play with when we try to compute this definite integral. Then after we have that definite integral computed, then we have simply a limit with an algebraic expression. And at this point, we're pretty dang good at working with those. But we have here again from 1/10 to t of 1 over x dx. And in this case, the antiderivative of 1 over x is the natural log. So now we can rewrite this as the limit as t goes to infinity of the natural log, or the natural log of absolute value of x from t to 1/10. And in fact, in this case, since our values are all positive, they're starting at 1/10 and going to t. I actually don't need the absolute values. That doesn't matter too much. Let me now plug these in. So we have the limit as t goes to infinity. Plug in a t here. I get the natural log of t, and then minus the natural log of 1/10. We have a very similar situation as we did previously, and this will happen a lot, right? Because in many of these improper integrals, one of our side is an actual value, and so this is just going to be a constant when we plug it into any algebraic expression. The interesting part we need to analyze is what happens with that non-constant part. In this case, the question now becomes, what happens to this expression as t goes to infinity? Specifically, as t goes to infinity, what happens to the natural log? And actually, as t goes to infinity, this term goes to infinity also, which means this is unbounded. What we would say in this case, because we cannot find a finite value, this algebraic term, or the term with the t, goes to infinity or negative infinity. Anytime something weird is happening, we can't calculate a finite value, we're going to say that we can't compute the value of this improper integral. It's divergent. So the big conversation becomes in this section is, what is convergent and divergent? And hopefully in your head, you're kind of thinking at this point, well, okay, so 1 over x is actually divergent. It still has this like horizontal asymptote at 0. It looks like it goes to 0, but apparently not fast enough to satisfy this definition of the improper integral. But then 1 over e to the x converged. What's so special, or what functions in between those two? How fast do you have to go to 0? That's actually a really important big conversation we're going to tackle. But one thing before I kind of get in a little bit of that conversation with some simple rational expressions is to importantly say that in this case, the 1/10, or in the case with 1 over e to the x, the negative 2 wasn't really important at all. It did in the first case actually help us with how to, it gave us that exact value of 7.2. I mean, for instance, if we, for 1 over e to the x, went back to negative 4 to infinity, it's still going to converge, and it would have a value of something like 54.6, because it would end up being e to the 4th. But that's not the important part. The important part is generally what functions are going to 0 fast enough so this area converges, or the improper integral converges. To help us with this conversation of which functions diverge and which functions converge, what I want to do is look at these simple rational expressions of 1 over x to the p and see if we can make a general statement. This won't be a formal proof of this, but a really intuitive argument for a really important properties of these types of functions right here, or these improper integrals. In this case, I have 1 over x squared. In this case, I have 1 over x to the 1/2, or the square root of x. And I'm looking at exactly the same interval. And again, to state, it doesn't really matter what these values are, though since there's a domain restriction happening at 0, let's keep it positive so things don't get crazy. But what I want to do is see if this one diverges or converges and this one diverges or converges, and if we can kind of develop an intuitive argument for what p values for this 1 over x to the p, which of those converge and which of those diverge. Starting here with 1 over x squared. In this case, this is a simple antiderivative, so I'll have the limit here as t goes to infinity. We add 1 to that exponent to get negative 1 divided by negative 1, and we're going to evaluate that from t to 1. And so our limit as t goes to infinity is of, if I plug in a t here, I'm going to get 1 over t to the negative 1, 1 over t. So this becomes negative 1 over t minus plugging in a 1 right here, and I just get a -1 from that. Clean that up a little bit, make that a positive. Now as t goes to infinity, this right here goes to 0. And so this actually gives me out a value of 1, meaning this improper integral converges. Playing the same game over here, let's do this integral. We have the limit as t goes to infinity. So we got -1/2 add 1, so we get x to the 1/2, and then we're going to divide by 1/2, which we know is the same as multiplying by 2. Let's keep it like that for half a second. And now we get the limit as t goes to infinity, and let's plug in t here. So I'm going to write this as 2 times the square root just to make it look a little bit easier there. Again, the actual values aren't important to me. I want to kind of think about both of these examples kind of more globally. So, but anyways, this is 2 times square root of x. So this is 2 times the square root of t minus 2 times the square root of 1, which is just 1. So we have that value right there. Everything's looking good. But now as t goes to infinity, so does this term, the square root of t. As t goes to infinity, this goes to infinity. So this diverges. So to generalize this, we now have 3 examples of this type. This is an important type. We're going to have a comparison test later, and these simple rational expressions can really help us quickly move through and identify whether a function converges or diverges. But importantly to say why this converges is because after I take the indefinite integral or find the antiderivative, I'm still left with this rational expression. And if you think about this, the anti-power rule adds 1 to this. So as long as this negative right here, or this p-value, which is the same, right? As long as that negative is more than -1, when I add 1 to it, I'm still going to have this rational expression. So when I plug in infinity, I'll have my variable will be, and my variable t in this case, will be in the denominator, and so that expression will go to 0. Now, if that p-value is less than 1, in this case a 1/2, so x to the 1/2, which becomes x to the -1/2, when I do the anti-power rule and add 1 to it, then I'm going to get an expression that's not a rational expression anymore. I'm going to give a term, the term that I plug the infinity into is not going to go to 0. Therefore, generally speaking, I would say if this p-value is equal to 1 or less, it's a divergent improper integral. And if my p-value in this case is bigger than 1, then it will be convergent. Throughout this section, this is a really important fact. Keep this in your back pocket, especially when we get to the comparison test and more difficult integrals. When we're trying to identify whether they're convergent or divergent, we can compare them to expressions that look like this. And then finally, you might be thinking, oh man, here's one thing about these improper integrals. They brought back the limits, which isn't great, but at least they're not all of those crazy integration stuff that we've done previously. Well, bad news, we still have all of those tricks, and we're going to need a lot of them to tackle the kinds of improper integrals that are interesting. And again, it's all about these rational expressions of sorts. Functions that have asymptotes or horizontal asymptotes that go to 0 are the most interesting, because if you have something like a polynomial and as you go to infinity, you'd be like, of course it's divergent because the value gets infinitely large at some point. So the kinds of functions we're going to look at especially lend themselves to integration by parts. So in this example, we're being asked to determine whether the improper integral from 1 to infinity of the natural log of x over x cubed is convergent or divergent. And again, what we're going to do is actually try to see if it converges. That's our way of doing this. If we get a value, it's convergent. If we can't get a value, it's unbounded, goes to infinity, then we say it's divergent. And just for fun again, I want to look at the graph of this function just to see if I get an idea of whether it is convergent or divergent. And I would say, looking at it, it looks like it's possibly convergent. It doesn't look ridiculous. It's going to 0 as x goes to infinity. But let's now do the work. Again, the first thing we want to do is rewrite this as this limit statement. So the limit as t goes to infinity of the integral from 1 to t of the natural log of x over x cubed dx. And now looking at this, this is obviously not as simple as 1 over e to the x or 1 over x squared or 1 over the square root of x. So what we're going to do is use integration by parts on this. Again, we're using Liate. Logarithms are at the beginning, so I'm going to have this be my u. And just to kind of forecast what this is and why this will work great, and you've probably seen examples of this, I want this to be u because the derivative of natural log of x is 1 over x, and that's going to play really nice with this. Even when I anti-differentiate it, this is still going to be a rational expression, so my new integral will be easy to work with. But I digress. Let's play with it. What I often do with these, just because there's a limit and this definite integral we're dealing with, if I have something more difficult, I'm going to play with this on the side. So what I'm going to do is actually do my integral work over here. Once I'm done with that, then I'll bring my expression in and finish with my limit work. And as I said, I'm going to use integration by parts. So I'll set this up. My u is going to be the natural log of x. I like writing in my pieces here, so let's do this. And I also, by the way, I write my functions up top and my differentials down bottom for both of them. That might be a little bit different than what you're used to. It's not a huge deal. But so I got u dv, and so my dv is this part right here. So it's x to the negative 3 dx. Differentiating here for my du is 1 over x dx. Anti-differentiating here to get x to the negative 2 divided by negative 2. I'll just write that right there. And just to clean this up to make it a little bit easier, I'm just going to write this as negative 1 over 2x squared. So then this integral, given that setup, is u times v. So it's the natural log times negative 1 over 2x squared. So I'll write that as negative natural log of x over 2x squared. And then here I'm going to be subtracting the integral of v du. When I multiply these two together, well, that negative, I'm just going to bring out here and make that a positive. And I'm going to get 1 over 2x cubed dx. I also don't want to forget about this is a definite integral, so I want this from 1 to t here. And then to finish this off, this is 1/2, I could pull that out, x to the negative 3. And so let's just jump in and do that. So I get the natural log of x all over 2x squared, evaluated from 1 to t. And then here I get plus, and then a 1/2. X to the negative 3 becomes an x to the negative 2, and I'm going to divide that by negative 2. And again, integrating from 1 to t. All right, so I've done the work of the definite integral part. What I'm going to do now is actually, I'll rewrite this first. So I'm going to rewrite this first as all one big expression evaluated from 1 to t. So then I can kind of start focusing in on this limit. So here we go. We have the limit as t goes to infinity. And there's nothing really to play with right here yet. I'll just leave this as the natural log of x over 2x squared plus, and then that part becomes, I got an x squared on the bottom. I have a negative actually, so we'll subtract this minus 1 over 4x squared. And that's all going to be evaluated from 1 to t. What I'm going to do now, just because of space, I think we've rewritten that. I'm going to erase that and then start working on the limit work, which first starts with plugging in t into these expressions. All right then, so let's now plug in our bounds here. Again, we can't do any limit work until we plug in these bounds. So we have the limit as t goes to infinity, and I plug a t in this expression first. So this is negative natural log of t over 2t squared minus 1 over 4t squared. Okay, then I'm going to subtract what happens when I plug this in. This won't be too hard. When I plug in a 1 to the natural log of 1 is 0, so that term just goes away. And when I plug in a 1 here, I'm just going to get a minus 1/4. Now, we're in the game of the limit world, and the one thing we can't forget about, and our big reason outside of integration by parts and making this a little more complicated than my other examples, I want to make sure you remember of how to argue some of these more difficult limits with infinity being involved, specifically remembering L'Hopital's rule. In this case right here, these two terms in this limit aren't a big deal. And remember, when you're evaluating a limit, an expression that has multiple terms, each term can be attacked with the limit separately. This is a constant. This is a positive 1/4. That's easy. This is right here, 1 over 4t squared. We know as t goes to infinity, we know that goes to 0. We need to analyze this right here. What we can do, because as t goes to infinity, each of these are unbounded. This goes to negative infinity and that goes to positive infinity. What we can do then is apply L'Hopital's rule to this term right here specifically. And again, I always use this little L to denote that what I'm doing here, making these limit statements the same, is applying L'Hopital's rule. It's a little bit loose because I haven't split this limit up exactly, but I think at this point, that's not really a big deal at all. So in this case, we have the limit as t goes to infinity. I'm applying L'Hopital's to this. This becomes 1 over t, and then this becomes 4t. If you remember, L'Hopital's rule is just you saying that if you have these unbounded, if they go to 0 or if they're unbounded, the numerator and the denominator respectively, then you can apply the derivative to the numerator and denominator and not change the value of the limit. And that's the beautiful move right there. In this case, I'll just show this also, and I'll separate these statements. But this one, that goes to 0. That's not doing anything. This is just a constant, so when I apply the limit, it goes to 1/4. So I'll just use pink here just to denote that I've actually taken that limit, and we probably should put some parentheses around this so we know that the limit is only applying to this right here. And then this is pretty straightforward, just to write it out for us to make it easier. This now is easy to take the limit. This is the same thing as negative 1 over 4t squared, which look at that. It's exactly the same as that one. And then we have this plus 1/4, again, that we've already calculated. This limit right here as t goes to infinity, this goes to 0, giving us that the value of this improper integral is 1/4. And therefore, this is convergent. Which means this improper integral is convergent. It converges to the value of 1/4. And again, what we did here was we're doing exactly the same work as previously, though when dealing with this definite integral, we might need to use one of the more difficult techniques that we've recently used. In this case, I used integration by parts, but it could be trig sub or any of those other techniques that we've seen. Once I've done the work of finding that antiderivative, all I'm doing is plugging in t and my constant, or my constant and t if we're going to negative infinity. All that works exactly the same. After that, this has nothing to do with integrals anymore. It's back to the limits world. What you should expect as a beautiful tool when doing your limits is using L'Hopital's rule. And just to remind you of that property, L'Hopital's rule only applies to rational expressions where you have unbounded numerators and unbounded denominators that go to negative or positive infinity. That's a really, really important statement. Or they can go to 0 also. So if both your numerator and denominator are going to 0, then you can apply L'Hopital's rule. In these other cases, you'll often have rational expressions or constants that there's nothing to do with. Using something like L'Hopital's rule, reasoning your way through to find the value if you can, or you might find that those rational terms go to infinity, which simply means it diverges, which is definitely possible.